Hello and welcome to lecture 53 of the course Theory of Computation. In the previous lecture, we saw two NP-complete languages, click and vertex cover, which are both based on graphs. In this lecture, we are going to see yet another NP-complete problem called Hamiltonian path. Another difference in this particular lecture is that we are going to be talking about directed graphs. Okay, so what's a directed graph? It's simply put, it's a graph where the edges have directions. So in earlier lectures, our edges used to be undirected. So the edge from I to j would be the same as the edge from j to I. But now it is we have the edges look like arrows. So there are directions. So an edge from I to j need not be the same as an edge from j to I. So in an undirected graph, given two vertices I and j, there could be no edge between them, or there could be one of them, or there could be both of them. All of this is possible, right? So there are three possibilities, one of them, or four possibilities. Maybe no edge exists, edge from I to j exists, but j to I does not, edge from j to I exists, but I to j does not, or both of them exist, right? Okay, so that is about directed graphs. What is a Hamiltonian path? A Hamiltonian path, so I'll just erase these things. The Hamiltonian path is a path. So in the variant that we are going to see in this lecture, there are two designated vertices S and T. So let's say this is S, this is T, this is some A, this is B. Is there, so the question is there a path from S to T that goes through all the vertices in the graph? So in this particular graph that I have drawn over here, right, there is no such path, because there is a path from S to T that goes via A, but there is no path from S to T that goes through both A and B, right? Because I can do this S, A, B, but then once you get to B, there is no way to go to T. And from S, you cannot go to B or T directly. You can only go to A, but then once you go to A, you have to either go to T, in which case the path is over, or you have to go to B, in which case there is no way to get back to T. So this particular example does not have a Hamiltonian path. However, if let's say maybe another example, so S, T, A, B. Sorry, what's up? Let's say this is B. So in this case, there is a Hamiltonian path. So you can go, so S to T, you cannot take this because then you would have skipped A and B. But you can go from S to B and then to A. S to B and then, S to B and then to A and then A to T, right? So if you go from S to A, then A to B, then there is no way to get to T. But if you go from S to B, then B to A and then A to T, that's a Hamiltonian path, right? All the vertices in the graph are covered, right? So the Hamiltonian path is a path from S to T such that all the vertices in the graph are covered and exactly once. We don't want to repeat any vertex, right? And as a language or as a problem, it is given a three-tuple graph S and T, a graph G, S and T, where S and T are vertices in the graph. It is a yes instance if there is a Hamiltonian path from S to T, and it is a no instance if there is no Hamiltonian path from S to T. And this is NP-complete. Like in the previous lecture, what we are going to do is to do two things. One is to show that it is an NP, and second is to reduce a known NP-complete problem to Hamiltonian path. So showing that it is an NP is easy. This is the easy part, right? This is easy. We just guess, we basically guess a sequence of n minus 2 vertices. So let's say there are n vertices in the graph. We guess a sequence of n minus 2 vertices. So let's say v1, v2 up to vn minus 2. And then we just check whether S, starting from S, then v1, v2 up to vn minus 2 and then t, whether this forms a Hamiltonian path. So we guess a sequence and we just check whether this forms a Hamiltonian path. So we check whether this is a path. Is there an edge from S to V1? Is there an edge from V1 to V2, and so on? And we also check, are they all distinct vertices, right? And this verification takes polynomial time. So guess something and verify something, right? So this is an NP, right? So I don't want to spend too much time on that. The more interesting part is showing that 3-sat is reducible to Hamiltonian path. So the NP-complete language that we picked is 3-sat. So given a 3-sat instance, let's say phi, we have to construct GST, right, which is an instance of Hamiltonian path, such that this is a yes instance of 3-sat if and only if this is a yes instance of Hamiltonian path. In other words, phi is satisfiable if and only if the graph G has a ST Hamiltonian path, right? So let's see how to construct this. So the construction is a bit more involved than the vertex cover. So I'll mostly be explaining through pictures rather than writing. So let phi be a formula that has n variables and m clauses, and let the n variables be x1, x2 up to xn, right, and m clauses, right, m for Mary. And now we are going to see how to build the Hamiltonian path instance, right. So what we do is we have this diamond shaped structure for each variable, right. So we start with x1. So this, the top diamond stands for, corresponds to x1, right, as I marked here. So it starts with S on the top. So this vertex I am calling it S, this vertex is S, and I have this diamond structure. So notice that all this arrow is pointing downward, this arrow is pointing downward, right, this arrow is pointing downward, and this arrow is also pointing downward. So everything is pointing downward, and now there are these intermediate vertices, right, I am calling them intermediate vertices, sometimes I call them nodes, right, where I have both directions edges, right. So going from left to right as well as right to left, and there are 3m plus 3 vertices here, starting from, including the leftmost one and including the rightmost one, 3m plus 3 vertices here. Okay, so and there is a path from the right to the left and a path from left to the right, both directions there is a path. So between each of these adjacent vertices there is a arrow from left to right and a arrow from right to left, right. And why 3m plus 3, I will explain briefly. What we do is, after the first, so there are two endpoints here. After the endpoint we leave one vertex, we skip one vertex, and the next two vertices we call them a group corresponding to C1, where C1 is the clause, right, and then we skip another vertex, and the next two vertices, right, so I have not drawn the next two vertices, this corresponds to the clause C2, right, and we skip another one, and the next two will correspond to clause C3, and so on up to m clauses, and then another vertex we skip, and the last vertex would be the rightmost vertex, right. So you can check the count and verify that this indeed gives us 3m plus 3 nodes. Okay, there will be 2m for the clauses, and the side and at the either end the number will be m plus 3, so we get 3m plus 3 nodes, right. So once again we have a diamond starting from S on the top, going down to left and right, and then again converging to another one, and then there is a series of 3m plus 3 nodes, and there is a path from left to right as well as right to left, and we have identified some correspondence between two vertices and a clause, and then skip another one, then the next two corresponds to C2, and so on, right. And for each m clauses I have two vertices, and they are all separate, and the same thing repeats in the next diamond for x2. So the top of the x2 diamond is the bottom of x1 diamond, right, which is the same vertex. And same thing, I have path from left to right and right to left, and I have identified boxes similarly for C1, C2, etc. And so on, so on, so on. And finally, I have the nth diamond corresponding to the variable xn, right? And similarly, I have these boxes, right? So maybe I can just draw them. This corresponds to C1, and so on. This corresponds to C1. And the bottom vertex of the nth diamond is T. So top vertex of the first diamond is S, and the bottom vertex of the nth diamond is T. Right. So, and this is not all. There is some more vertices that are going to come in a bit. But let us see what options do we have. Now, suppose ignoring the vertices on the right side for a moment, just these diamonds and the vertices in the diamonds, what is the way to start from S, cover all these vertices and come to T, right? So, one way would be to start at S, go left, then cover all these intermediate vertices going right and then come down, right? So, this is one way to cover this diamond. Another way to cover this diamond is to go right, go to left, covering all these vertices and then come down. Right. So, the two ways to cover the top diamond, one is do this, another is do this. So, the first one we call it a zigzag motion, right. So, this is zigzag. The next one we call zag-zig. Right. I don't think zag-zig is a word, but it will be a word for just this proof. Right. So, these are the two ways to cover this diamond. So, starting from S, the idea is the following. This zigzag will correspond to the variable being set in the to true, and the zag-zig will correspond to the variable being set to false, right. So, that is the kind of correspondence that we will get to, right. So, starting from S, we could do this, which is zigzag or zag-zig, and as I said, zigzag corresponds to the variable being set to true and zag-zig corresponds to the variable being set to false. So, how that correspondence comes, we will see in a bit, okay. And same thing we can do for x2 also. Once we do something and come here, then we can do the same thing, but we also, there is no compulsion to do the same thing as x1. I can zigzag on x1 and then zag-zig, I can zigzag on x1 and then zag-zig on x2, no issues. So, now like that, so I have two choices in each diamond, right. I could zigzag or zag-zig, and there are n such diamonds. So, we have 2 power n ways to start at S and reach at T, right. We have 2 power n ways to start at S and reach at T if we ignore these vertices that I have not talked about so far, right. So, that as of now, if we ignore these vertices, if we think that these vertices do not exist, the vertices in the right side, there are 2 power n Hamiltonian paths, not just one, there are 2 power n Hamiltonian paths from S to T. But then these vertices are going to bring some interesting things into picture. So, let us see how these vertices are going to like influence the thing, right. So, if we need to like, we cannot just add these vertices, because if we just add these vertices without a way to access them, then there is not going to be any Hamiltonian path, right, because we will just go from S to T like this, but we have to reach these vertices somehow. So, what we do is the following. So, suppose, so consider this figure, right, consider this figure. So, suppose a variable x1, let us say this is the diamond of x1. So, I have zoomed it a bit, right, I am looking at the diamond of only x1, this is only the diamond of x1. Suppose x1 features in the class 1, okay. So, then what we do is, in the middle row of vertices of x1, right, there is this box that corresponds to C1, right, that we said earlier, that we marked earlier. In that box, the left vertex, from the left vertex we put a directed edge to the C1 vertex. Okay, before that, let me just tell you, there are going to be m vertices in the right side or somewhere, right, and these correspond to the m clauses. So you have n diamonds, one for each vertex, sorry, one for each variable, and you have m vertices, one for each clause. One diamond for each variable and one vertex for each clause, right? So let us take C1 and how we are going to connect C1 to this, right? So if x1 appears in C1, then what we do is we look for the box marked C1 in x1. The first vertex from the left, we put a directed edge to C1, and we put a directed edge from C1 to the second vertex, right? This is what we do if x1 appears in C1. If x1 appears in C2, we will do the same thing. But suppose for instance x1 complement appears in C2, right? So then we do the same thing, but the only difference is that if x1 complement appears, the order is reversed, right? So the first vertex, we put a directed edge from C2 to that first vertex in the box, and the second vertex we put a directed edge from the vertex to C2. So if the literal is the positive literal, from the first vertex we put a directed edge to the clause, and second vertex receives a directed edge from the clause. If the negative literal appears, from the first vertex, sorry, from the clause we have a directed edge to the first vertex, and from the second vertex there is a directed edge to the clause in the case of a negative literal, right? So this is the example. When x1 appears in C1, this is the thing, and x1 complement appears in C2, this is the thing, right? And from the box marked C1, we are only going to connect to C1 and nothing else, and from the box marked C2, we are only going to connect to C2 and nothing else, right? So that's why we have separate earmarked boxes for each clause, right? And this is something I already mentioned. We can go from S to T. If we ignore the clauses, there are 2 power n ways to go from S to T, right? This is something I already mentioned. Basically each diamond you can zigzag or zag-zig. Now how are we going to include these clause vertices? How are we going to include these vertices, right? So I have already marked some blue edges based on what I said. So here, as per the figure, x1 appears in clause 1, right? Because there is first vertex goes to clause 1, second, and from clause 1 you get back to the second one. And x2 complement appears in C1 because the order is reversed. From the first vertex is receiving a directed edge from C1, and second vertex is sending a directed edge to C1. So here x1 appears in clause 1 and x2 complement appears in clause 1. Now if x1 appeared in clause 2, you will have to connect something like this, right? So now how are these? Now we have the Hamiltonian path, and how are we going to incorporate these clause vertices, right? So the way we are going to do it is, suppose x1 features in C1, right? So then in clause 1, right? So then if we are zigzagging, it is easy. Zigzagging means this. It is easy because we can start from S, come to the left side, and as we are coming here, we enter this box for C1. Then we move to the clause vertex, and then we come back to the next vertex, and then we continue our zigzag journey, right? So that is how we will accommodate or will incorporate the clause vertex. Now suppose x2 appears in C2, or x2 complement appears in C1, right? That's what we said, right? That's why this is marked like this. Now if we are, x2 complement appears in C1. Now suppose we are zigzagging, right? So we come here. Now there is no easy way of covering C1 from this, because the edges are marked in the opposite order, in the wrong order. If it was marked in the other way, we could have done this, but now the edges are marked in the opposite order. But if we are zag-zigging, this is the correct order. We can come from the right side, visit C1, and then come back to the first vertex in C1, and then do this. So x1 can cover C1 if we are zigzagging in x1. x2 can cover c1 if we are zigzagging in c1 in the diamond for x2, right? So again, I am going to say this. Zigzagging indicates that x1 is said to be true, and zigzagging indicates that x1 complement is set to true, or in other words, x1 is set to false, right? So zigzagging means I can cover the clauses if x1 appears in the clause, right? So this means zigzagging means x1 appears in the zigzagging means like this, and the way we have marked this clause is when x1 appears in that clause. So when we are zigzagging, we can include all the variables where all the clauses where the variable appears as the positive literal. If we are zigzagging, we can include all the clauses where the variable appears in the complemented form, right, or in the negative literal, right? So if we are zigzagging, we can cover the clauses in which xi is present, and zigzagging we can cover the clauses in which xi complement is present. And that is the construction. So I have explained the diamonds, the top and the bottom S and T, and how for each and these clause vertices and how these are connected, right? Now one point that I'm somewhat glossing over is that it's clearly a polynomial sized construction, and it's a very repetitive structure. So we can build this thing in polynomial time for sure. So as an exercise, you can see how many you can count how many vertices are there, and think why this is producible, or why this instance can be generated in polynomial time given the Boolean formula. Now what remains to see is the correspondence, that is, phi is satisfiable if and only if this graph has a ST Hamiltonian path, right? This graph means the entire graph including the clause vertices by the side. So suppose this is, so let us see, suppose suppose the formula is satisfiable, means that you can set variables to true or false such that every clause has a true literal, right? So now all that we do is this. So now we have to show that the graph has a Hamiltonian path. Now suppose, so all that we do is that how do we get the Hamiltonian path? So we check the satisfying assignment, right? So the assumption is that there is a satisfying assignment. Suppose x1 is true in the satisfying assignment, we zigzag. Suppose x1 is false, we zigzag, right? Now the thing is this. Now how are we going to cover the clauses? Now suppose C1, so as per the drawing here, C1 contains x1. Now so C1 contains some true literal. So suppose the true literal in C1 was x1, right? Which means x1 was set to true in the assignment, satisfying assignment. So then we would be zigzagging. So now we come down to the left side, and then when we zigzag, we include C1. But if x1 is set to false, then we would be zigzagging and we cannot cover C1. But suppose C1 is covered by x2 complement, right? Because x2 complement is there in C1, right? That's how this is connected. Which means x2 complement must be true, which means x2 should be set to false by the satisfying assignment, which means we will zigzag in x2, and when we zigzag, we can naturally visit C1 and come back and then continue our zigzag journey, right? We could do this, right? So like this, because it's a satisfying assignment, every clause has a literal that is true. And whenever we reach the literal, we take a detour to the clause vertex and then come back. And because of the way the variables and the gadget is set up, the detour allows us to go to the clause vertex and then come back to the next vertex without missing anything and continue the zigzag or zigzag path, right? So that's how we are going to show that. We are going to show the Hamiltonian path, and finally we keep going down. Finally we reach T, and in the meantime we would have covered all the variables, and we would have also have covered all the clauses, because each clause is satisfied by some variable, and whenever we cross that variable or literal where that clause is satisfied, we make it a point to cover that clause. So all these clause gadgets also will be covered. Right? Same thing I have written here. There exists a true literal for each clause. We start from S and move down. If xi is set to true, we zigzag. If xi is set to false, we zigzag. Right? If xi is set to false, we zigzag. And each clause can be covered by a detour. That gives a Hamiltonian path. Now the opposite direction. Suppose there is a Hamiltonian path. Now how do we show that there is a satisfying assignment? So suppose there is a Hamiltonian path. Now suppose the Hamiltonian path worked in the manner we just described in the forward direction. Suppose it zigzags or zigzags, and whenever there is a clause, you make a detour and immediately jump back and continue. Suppose this is the way it happens. Then it's fairly clear, right? Suppose this is the way the path is, that every time we zigzag or zigzag, and whenever there is a clause, you make a detour, and that's how you cover all the clauses. In this case, so you just do this. If a variable is zigzagging, we set that variable to true. If a variable is zigzagging, we set that variable to false. And by the same argument that I just made for the forward direction, this implies that because we cover all the clause vertices, this implies that every clause, so we can only cover the clause vertex if we are moving in the correct direction. So which means if we set zigzag to true and zigzag to false, what we end up with is a satisfying assignment, right? Because we are able to cover all the clauses, and the only way we can cover all the clauses is if our movement is in the correct direction. So if we have to cover a certain clause C from a certain variable xi, right? Either we should be zigzagging on xi with xi present in C, in which case we set xi to true, or we should be zigzagging on xi with xi complement present in C, in which case we are setting xi to false. So if the path is of this form, where we start from the top, we make a detour and come back to the same path, come back to the same diamond and then continue, then we know how to generate the satisfying assignment. We set the zigzagging variables to true and zigzagging variables to false, right? Suppose G has an ST Hamiltonian path, right? If the path is normal, this is what I call normal, meaning it goes through all the vertices diamonds in order from top to bottom, then we set each variable to true false as per the zigzag or zigzag. So maybe I'll just write that as per zigzag or zigzag, right? And as by the explanation that we just gave here, this means that all the clauses are satisfied. Now there is a certain assumption that we made here. If this path is normal, right? So, and this is fine. Is there a way in which a path may not be normal, right? So the only way that we may not be normal is, suppose we start here, then we go to a clause, then instead of re-entering back to the first diamond, we re-enter back some other diamond, and then we continue something, and then maybe we come back to the first diamond through some other clause, right? So is this possible, right? So if we know the Hamiltonian path takes this normal standard zigzag or zigzag by taking detour, it is okay, that we know. Now the only question is, what if it does this and then you go somewhere and then you go somewhere and sometime later you come back, and then now is it zigzag or zigzag? How do you determine, right? So the point is that I am going to argue that such paths which are not normal, like you enter a clause and then from there you go to some other diamond and then later you come back to the original diamond, this kind of situation cannot happen, right? That's what we are going to argue, and this is because we have these buffer vertices between these clause boxes, right? So these buffer vertices are going to play a role. So let's see how. So again I have zoomed in figure. How can a path not be normal, right? That can happen if we leave a certain diamond, you go to a class and then you re-enter some other diamond, right? So how can this happen? Let's say you exit the 5th diamond and enter the 10th diamond, and later maybe from the 15th diamond you go back to the 5th diamond. But can this happen? We are going to say that if this is attempted, then it will not be a Hamiltonian path. Let's see why. So if we have this arrow A1 to Cj, there are two possibilities. One is that this diamond A1 and A2 are grouped together and A3 is a separator, right? A1 and A2 are grouped together and this is a separator. So now the question is how are we going to come back to A2? Right? At some point A2 needs to be covered if it's a Hamiltonian path, right? So A2 is connected to, right? So now if this is the box, this box corresponds to the second clause, the clause Cj, which means there is an arrow coming from Cj here, and also A3 connects to A2, A1 connects to A2, right? So if this is the box, how can we enter A2? Right, so I am actually discussing the second case. If this is the box, A3 is a buffer vertex or a separator vertex, right? So we can re-enter A2 from A1, but then A1 we have already covered. We somehow reached A1, then went to Cj and then went to B2. Now we cannot re-enter A2 through A1. We cannot re-enter A2 through Cj because Cj is also already covered. So the only possibility is the only other vertex that is adjacent to A2 is A3, right? So suppose we enter A2 to A2 through A3, then there is an issue because there is no next step now, because the neighbors of A2 are A3 from which we just came, then A1 which is already covered, or Cj which is also already covered. So there is no exit out of A2. So these two cannot be one block. So the other possibility is A1 and the one left to it form a block and A2 is a separator vertex. Now if A2 is a separator vertex, it is not connected to any cross vertex. The only way we can re-enter A2 is through A1 or A3. But A1 we have already visited. Now if we enter through A3, there is no way out again. So I am talking about this case when A2 is a separator, because if we enter through A3, we can only go back to A1 which is already covered, or to A3 which is also we just came from. So A2 to A3 is also like there is no way out. So this is why if A2 is separator or A3 is separator, whatever be the case, we cannot leave a diamond and then enter some other diamond. This will not be a Hamiltonian path. What we just said is, if we do that, then we argued that there is no way to cover A2, or if we try to cover A2, we cannot come out and reach T at the end. There is no exit option. Hence, this means that the only possible Hamiltonian paths are the ones where we start at the top, we zigzag at a diamond or a zag-zig at a diamond, and then again zigzag or zag-zig. At wherever point you go to a clause and then come back immediately, rejoin immediately and continue. This is the only paths possible, and for these paths we know how to deal with it. Like if it is zigzag, we assign true, and if it is zag-zig, we assign false, and that, as we already saw, results in a satisfying assignment. Hence, if there is a Hamiltonian path, it has to be this normal structure, and that gives us a satisfying assignment. So that completes both directions. If the graph has if the formula is satisfiable, we have a Hamiltonian path. If the formula is not, if the graph has a Hamiltonian path, we have a satisfying assignment for the formula. So that completes the correspondence. Right, that completes this correspondence, and that completes the reduction. And this shows that Hamiltonian path is NP complete. Okay. Now, two more small things before I end this lecture. One is that we can take the undirected Hamiltonian path. So far we talked about directed Hamiltonian path. So undirected Hamiltonian path is the same problem in an undirected graph. This is also NP complete, right? So undirected graph means now, so over here in several places we were using the direction critically, right? So like we all have directed edges, and so the direction was playing a key role. But in undirected Hamiltonian path, we do not have that. But we can reduce from, right? We can reduce from so in all these cases, showing that it is in NP is easy. Now we need to reduce from some NP complete problem. Here we can reduce from the directed version of the problem, right? So this is there in the book. You can try to read up. So basically we replace each vertex with 3 vertices or something like that, so that the direction is somehow like if a graph, if a directed graph has a Hamiltonian path, the resulting, like we construct an undirected graph that also has a Hamiltonian path, and if and only if, both ways. The second thing is Hamiltonian cycle. So what is a Hamiltonian cycle? It is a cycle, it's a directed cycle that goes through all the vertices exactly once. So there is no beginning or end, it's a cycle that goes through all the vertices exactly once. This is also NP complete. This is not there in the book, but nevertheless I ask you to think about it. So one thing that you may want to do is, if a graph has a Hamiltonian path, like let's say this is the graph and this is S, right, and this is T. One thing that may be tempting is to, so we know that one thing that it may be tempting is to connect T to S using a directed edge. So now if this original graph has a ST Hamiltonian path, then along with this new edge, this forms a Hamiltonian cycle. But then if there is a Hamiltonian cycle, should there necessarily be the ST path? Should there necessarily be an ST path? Not necessarily, because the Hamiltonian cycle may not use this new edge. It may be just going through some other way. So there need not be an ST Hamiltonian path, while there will be other Hamiltonian path with other start and end vertex, right? Hence this construction is not enough, but we can add a new intermediate vertex here. Let's call it R, and where we had 2 directed edges, T2R and R2S. Now if the new graph has a Hamiltonian cycle, then it necessarily has to have a Hamiltonian path from S to T, because there is no other way R is getting covered. So this is the basic idea, but I leave it to you to think about this and work out the details. So that's it for lecture number 53, where we saw that Hamiltonian path is NP complete, right, where we reduce from 3 set by using this big reduction with interesting gadgets. And that's all from lecture number 53. Next lecture we will see yet another NP complete problem. Thank you.